Hello! In our most recent Further Maths tutorial, we looked how to find the area enclosed by a polar graph, and today we're taking it one step further by finding the area enclosed by multiple polar graphs. The content we're covering today sometimes takes a bit of time for students to wrap their heads around, and a big part of that is due to the fact that polar integration rewrites some of the rules people are familiar with from their previous experiences with Cartesian integration. However, I therefore want to start by reminding you what happens when we do Cartesian integration so that we can compare and contrast that with our approach for these harder polar integrals. That way we can be conscious of which decisions we take are ones we normally would do anyway versus the decisions we take that are different now that we're dealing with polar integration. I want to start by considering situations that involve two Cartesian curves like this and an area that could perhaps look like this. For argument's sake, let's say it extends from 1 to 3 on the x-axis. Now, hopefully by now people are aware that when you integrate with respect to x, what you're finding is the area between a curve and the x-axis. So therefore, if we were to start by integrating f of x, starting at x equals 1, we would be finding the area such as this. And that would make sense as that is all area that's within our shaded region. However, this would change once we go beyond our point of intersection. Let's say the point of intersection is at the point where x equals 2, and if we were to continue integrating f of x beyond x equals 2, then the problem is that would include some area that's not within our shaded region. Therefore, the point of intersection in this scenario acts as a changeover point, where we go from integrating f of x from 1 to 2, so therefore writing something like this. And that would find this area like this, and then we transition over to then integrating g of x, because then you'd notice if we're finding the area between g of x and the x-axis, that is once again only including area that we care about. And therefore if we integrate g of x between 3 and 2, like this, then that would find this area here, and therefore meaning if I want to find this entire shaded region, I just have to add the results of these two integrals together. Cool, that's what happens when we're doing Cartesian integration. However, the thing to bear in mind is that we're thinking about up and down to know what region we're finding, and thinking about left and right to know where we start and stop, because we're integrating x's specifically. However, when it comes to integrating polar coordinates, you're integrating thetas, and therefore as a result, instead of thinking up and down to work out which area we're finding, you're more thinking about the area enclosed between the curve and the pole, and instead of thinking about the area being generated by travelling from left to right, we're now thinking about the area being generated by travelling anti-clockwise. So let's take a look at a scenario now involving polar coordinates with two polar curves. So let's say we've got a diagram that looks like this. We've got the two curves r equals f of theta and r equals g of theta. And for both of those curves, we've been given an interval, or a domain if you will, for theta. As I just mentioned, polar graphs are generated by travelling anti-clockwise about the graph rather than travelling from left to right. And therefore we need to have our brain switched on when considering what values are representing what parts of the graph. For instance, if we're talking about r equals g of theta, theta equals 0 is talking about specifically this point down here. Because, of course, if we're on the initial line, we have not rotated away from the initial line yet, which is what theta is measuring, how far anti-clockwise we have to rotate away from the initial line. And then what happens as we make theta bigger, we travel along the graph anti-clockwise until we get to this point all the way over here, which would be where theta equals pi over 2 for the graph of r equals g of theta. Whereas for r equals f of theta, we've been told actually we're starting at theta equals pi over 10, which kind of makes sense because you can see there isn't really a early point where it's starting on the initial line. There is admittedly the point over here down here, but that's not where theta equals 0, because we know once we start at theta equals 0, we have to travel anti-clockwise from that point, and there's nowhere to really rotate anti-clockwise from beyond there, because all the graph is clockwise from that point. So therefore, actually, that's why they say we're starting at theta equals pi over 10, which is this point over here. This makes sense because if you're then to draw a straight line from the pole to that point over there, then you can see that this angle would be something that's roughly pi over 10. And so therefore, of course, a reminder, this is also how theta values are measured for particular points on a polar graph. Therefore, by the process of elimination, if we travel anti-clockwise around that graph from theta equals pi over 10, then it implies that this other endpoint for this graph of r equals f of theta is the point where theta equals pi over 2. Cool. Now that you're aware of which part of which graph is formed by which values of theta, we can now start thinking about regions. So let's say we wanted to find the area of this shaded region here. We could start by considering what would happen if we integrated the curve represented by g of theta. Of course, if it's polar integration, we don't just integrate it, we have to do half lots of the integral of g theta all squared, and then we're integrating with respect to theta. Now, if you started with a limit of 0, that means we'd be starting down here. But then if you're doing polar integration, reminder, you're not finding the area between the curve and the x-axis, you're finding the area enclosed between the curve and the pole, which looks something like this as you're generating the area. So far, so good, because as you can see, all that area that I'm generating is part of the shaded region that we want. However, just like before with the Cartesian situation we were looking at, the point of intersection represents a situation where all this changes. If we say that point of intersection is where theta equals pi over 5, if we use a theta value for our limit of g of theta's integral that's bigger than pi over 5, then we've got a problem, because we'll be trying to find the area between the curve and the pole, which will look something like this, and the problem is that's including area that's not part of the shaded region. So therefore, we've got to stop integrating g theta at that point of intersection of pi over 5. And therefore, that means we're doing this area here when we're doing that first integral. As you can see, though, we haven't found the entirety of the shaded region that we wanted to find. And so therefore, now admittedly, this is the part that some students find it a bit difficult to wrap their head around initially from a visual point of view. But if you consider the graph of r equals f of theta, you'll notice that extra little bit of area we need to find is fully enclosed by the curve r equals f of theta and the pole, because every point that's on the curve of r equals f of theta beyond theta equals pi over 5 has a direct line of sight with the pole within our shaded region. So therefore, that settles it. What we need to do is we need to do the polar integral of f of theta, which means we've got to do f of theta all squared and half lots of that integral with respect to theta. And therefore, if we do the integral from theta equals pi over 5 all the way until that curve ends at pi over 2, that will be finding this region here. Therefore, if we want to find the overall fully shaded region that we had before, all we've got to do is add these two integrals together. Cool. So that's the idea. Let's put this into practice with an example. So we've got two curves, we've got a shaded region between them, and we've got to find the exact value of that shaded region. So how are we going to do it? Well, again, you'll notice in the previous explanation, the point of intersection held an important part of the method. So the first thing we're going to need to do is find what that point of intersection is. So therefore, let's treat them like simultaneous equations and find that point of intersection. So as they're both r equals already, just set them equal to each other. That would be the easy way of doing it. And then solve the equation. Of course, in this case, it's going to be fairly nice. It's going to be a quadratic. And therefore, we are going to get theta plus 2 or theta minus 1 as our two factors, therefore leading to theta equals 1 or minus 2. Now, because we're in the interval 0 to pi over 2 and theta is in radians, of course 1 radian is between 0 and pi over 2, so therefore this is the point of intersection that we care about. That's interesting because it now means that if I want to find this shaded region, that point of intersection is going to provide the boundary between the two curves, and therefore the first bit of the shaded region, this bit here, is the area that's bounded by r equals theta between theta equals 0 and theta equals 1. So therefore the first bit of that area is going to be half lots of the integral from 0 to 1 radian of theta squared with respect to theta. But what about that second part of the shaded region? How are we going to find that? Well, you notice that bit of the region is enclosed by the curve of r equals 2 minus theta squared, and therefore we're going to integrate that curve between theta equals 1 and theta equals pi over 2. Of course, though, because it's polar integration, once again, we're having to square the function, integrate the thetas, and we've got half lots of that. So that integral as a whole, or that pair of integrals, I should say, will work out the area we want, and therefore the rest of the question is just a case of continuing on ahead and completing these integrals. So I'm going to take a factor of a half out the front to save me having to write that twice. And then in the second integral, it's just a case of multiplying the brackets to make it easier to do the integration. So therefore, of course, that's going to lead to 2 squared, which is 4, a minus 2 times by theta squared, which is 4 theta squared, and then we've got a plus theta to the power of 4. Luckily, that means this is actually quite an easy question, because it's just one of those classic add 1 to the power, divide by the new power scenarios in both cases. So we're going to end up with a third theta cubed, and then also we're going to end up with 4 theta minus 4 thirds theta cubed, and then plus 1/5 theta to the power of 5. Cool, and then we got to plug our limits in. Of course, that first integral is very easy. It's just going to be 1 times by 1/3, take away 0 to the power of 3 times by 1/3, which is just 0. And then the other thing is not going to be quite so nice. We're going to have 4 lots of pi over 2. We're going to have 4 thirds lots of pi over 2 all cubed. And we're going to have 1/5 lots of pi over 2 all to the power of 5. And then we're going to have all that with 1 plugged in. Simplifying that, as it did ask us to write the answer in exact form, we're going to end up with 1/2 lots of 2 pi. We're going to end up with something that doesn't look very nice in minus 1/6 pi cubed. We're going to end up with a plus 1 over 160 lots of pi to the power of 5. And then combining all the other fractions together, you're going to end up with minus 38 over 15. Of course, you could choose to then multiply out the brackets with the half if you wanted to, so the final answer would be then just pi minus 1/12 pi cubed plus 1 over 320 pi to the power of 5, and then lastly minus 19 over 15. There you go, we did it. So that's the first scenario I wanted to look at, but then there's also a second scenario we need to look out for. And that is the situation where we have area between two curves. Of course, once again, taking another look at Cartesian to remind ourselves of what we used to have to do before, if we wanted to find the area between the two curves of y equals f of x and y equals g of x, you'd have to do the area enclosed by the curve that's at the top minus the area enclosed by the curve that's at the bottom, because if you subtract them away from each other, that will then just leave you with the area in between. But instead of thinking of it as the area enclosed by the curve that's at the top minus the area enclosed by the curve that's at the bottom, it's more helpful to think of it as the area enclosed by the curve that's further away from the x-axis minus the area enclosed by the curve that's nearer the x-axis. The reason we want to do that is because then that makes it more clear what adjustment we have to make when we're doing polar integration. And if we want to find the area between two polar curves. Because of course, polar integration is not considering what's going on with the x-axis, it's considering what's the area between the curve and the pole. So therefore, if we want to find the area enclosed between two polar graphs, we've got to find the area enclosed by the curve that's further away from the pole minus the area enclosed by the curve that's nearer to the pole. Because if we subtract them from each other in that fashion, then that will leave us just with that area we want. Okay, so therefore we can have a go at putting that into practice as well with this example here. We've got to find the size of the shaded area, which according to the question is enclosed by the two polar graphs, and also the line theta equals pi over 6. As you can see, the only part of that area that's enclosed by a straight line is this bit here. So that's what they're talking about when they say theta equals pi over 6. Admittedly, the question is then a bit mean because it doesn't label which graph is which on the diagram. However, as these are graphs that you're meant to know about anyway for the polar chapter in further maths, we can use a bit of deduction to realise which one is which. Of course, you're aware, hopefully, that the number in front of theta is referencing the number of loops these types of graphs have. Of course, there's always the number that you can see. Those are the number of loops where we've got a positive values of r. But then there's also secretly another same number of those loops for where r is negative. But therefore we know that r equals sine of 3 theta is having to fit 6 loops between 0 and 2 pi, whereas sine of 2 theta is only having to fit 4 loops between 0 and 2 pi. Therefore, as r equals sine 3 theta is having to fit more loops in the same space, each loop would individually have to take up less room. So therefore, as we can see, this loop here is the smaller one. This must be r equals sine of 3 theta. And therefore the graph with the bigger loop must be the graph of r equals sine of 2 theta. So there you go, a little bit of a reminder of polar graphs while we're at it. Anyway, therefore if we want to find this region, careful. Don't think about the curve that's on top and the curve that's on the bottom. Think about the curve that's further away from the pole for the region we're finding. The curve that's further away from the pole is, of course, the graph r equals sine of 3 theta. If you take any point over the interval that we're going to be integrating over, every point on that curve is further away from the pole than the corresponding point on r equals sine of 2 theta. So therefore, if we want to find this shaded region, we're just going to have to do the polar integration of sine of 3 theta, so that's half lots of the integral of sine squared 3 theta. We're starting with this curve because it's the one that's further away from the pole, and integrating with respect to theta, and the limits are going to be from 0 to pi over 6. Pi over 6 was given to us in the question as the part where the area was ending, but then theta equals 0, well, logically you should know that r equals sine 2 theta and r equals sine 3 theta are starting at theta equals 0. Not necessarily as a fact off by heart, but just numerically you can see that if you plug theta equals 0 into both those graphs, you get r equals 0, and r equals 0 is the pole. Cool, and then we're going to subtract from that integral the integral of the other curve, the one that's nearer to the pole, which was sine of 2 theta. Of course, though, we've got to do the integral of sine squared 2 theta and have the half in front. But once again, we're going to go from 0 to pi over 6. All we've got to do is now do those integrals. Of course, we're going to have to integrate sine squared of something. So, of course, you're going to have to make use of the double angle identity for cos. So, therefore, a reminder, we use this identity that we rearrange to get the sine squared x as the subject of the formula, but then make the adjustment that although that's the identity for sine squared x, we've got sine squared 3 theta, so therefore that first thing is going to be secretly half minus a half. It was cos of 2x, but now it's going to be cos of 2 lots of 3 theta, so cos of 6 theta. And then making a similar adjustment with the other integral. So the integral from 0 to pi over 6 of half minus a half, and it was cos of 2x, but it's now cos of 2 lots of 2 theta. So that's cos of 4 theta. Cool, now we can go ahead and do that. I'm going to factorize the half out the front, and therefore that will leave me with half theta minus 1/12 sine 6 theta minus 1/2 theta minus 1/8 sine 4 theta. And of course, in both those cases, we're going to be plugging in the limits of 0 and pi over 6. Working all of that out, we can plug that stuff in. So of course, we've got the half out the front. Admittedly, we could simplify things a bit more actually before we plug the limits in, because the half thetas are going to cancel out. Isn't that nice? So we've got 1/8 sine of 4 theta minus 1/12 sine of 6 theta. That's me just multiplying out the brackets inside. And therefore then plugging that stuff in, we've got half lots of 1/8 sine of 4 lots of pi over 6, which would be 1/8 lots of sine of 2 pi over 3, which is root 3 over 2. Fairly nice. Minus 1/12 lots of sine of 6 lots of pi over 6, which is really nice because that is just going to be 0, interestingly. So that's actually very easy. And then if we plug the limit of 0 into both those functions, that also becomes 0. So therefore, after all of that, the final answer is root 3 over 32. Cool. That is the answer to that question, and that is how you can find the area enclosed by multiple polar graphs. Hopefully you found today's video useful, and I'll see you in a future video. At some point I will have a video exploring even harder questions for polar areas, because I know it's a topic that sometimes some students do find a little bit difficult initially, so therefore I think the more examples the better. Anyway, for now that'll do us. Goodbye.